And so I just wanted to maybe talk about that today in broad brush strokes, I guess. And so, where's this? Where are we? So, in terms of recap, pretty straightforward, I think. The idea, if I draw some pictures for myself, we've talked about D-naples, or this would be an L-napple, right? Sitting in the system, some kind of chimney, and this acting as a source, so that water that's flowing past here picks up dissolved components and carries it downstream. We use the idea that a porous medium, if you look at putting some ink in a porous medium, and you've seen these things before, so I'll kind of go through it quickly. If the initial if you put a blob of ink in a beaker or in a porous medium and look at the concentration profile in space, so this is C over C0, and you allow this flow to go downstream, then all the individual components spread out. And as you look at it downstream, this distribution, instead of being a Manhattan and a skyscraper, is some kind of different distribution. It's lower than it was, and it's much more spread out. And this process is really what we're attempting to replicate. And what we're attempting to replicate is we use a partial derivative equation, PDE. And it's this. Doesn't really matter what the equation is, but we use it anyway. And you've seen it before, all these components, this is advective velocity. Which is the Darcy velocity divided by porosity. This term here is dispersion coefficient. And it's equal to what we'd call, not plus, equals D star plus alpha VA. And so this is the dispersion coefficient. It's due to mechanical effects plus chemical effects. D star is equal to the chemical diffusivity of a compound in water multiplied through by some correction factor, which I think we called omega. And so we can define this. So this represents Fick's law, essentially, in place. And this represents mechanical dispersion. And the fact that we use this coefficient dl is because if you look at the skyscraper going to this Gaussian distribution, it looks like diffusion, a diffusion problem. There is diffusion in it, but there's also mechanical dispersion, which looks just like diffusion. It looks like diffusion in that it's attempting to be able to reduce the gradient. And so it's taking concentration and length, dx, if you can't see that, dx and dc. This is the gradient that's part of Fick's law. Right? Fick's second law says that the mass flux is equal to diffusion coefficient times the gradient of concentration with a negative sign on it. And so this is for chemical diffusion, and it's really just this part. But when we look at motion in groundwater, if it's in granular material, then the fact that this kind of spreading, this would be an individual trajectory of a particle of solute as it goes downstream, it tends to spread. And as it spreads, this peak has to be reduced from this, and this width has to be increased from this. It's a typical diffusion process. And so we recognize that with the diffusion equation, and this is accumulation. And accumulation has to equal mass in minus mass out. That's all it is. And last Tuesday, a week ago, we'd have made the point that this mass in minus mass out can come from two sources. It can come from advection, water carried with ink in it, physically carried into the element and then carried out, as in a beaker. So it's carried on the carrier fluid, which is water, and also a diffusion process whereby the mass is transported by its own potential, if you like. It goes from high concentration to low concentration. This is a very slow process. This is a very rapid process. In granular reservoirs, this is large, and this is trivial in comparison. And in clay reservoirs, this is tiny, and this is large in comparison. So they switch roles, depending on the media we are in. And we also made a point that this is a dispersion dispersivity. And it's multiplied by the advective velocity of flow. So if you double the flow rate, you double this component of mixing. And so it's controlled by the advection in the system. And so, yeah, classic deal. I'm going to recap it, and I'm going to run out of time to talk about what I wanted to talk about today. But I think it's probably worthwhile mentioning. I mean, just to kind of summarize what the last little components were. So if we look at a core, a very good picture. And you can look at this behavior. That is, if you have relative concentration, C over C0, it's 1. And if you have some input function, so in other words, if the input into this upstream face, which has a length, and it has an advective velocity, then if you have, again, relative concentration, and that relative concentration with time, so this with space, this is with time, and if that concentration is nothing, and then there's a spill, it's dissolved in the water, and then that continues, so it gets turned on at some time t0, then you'd expect that this would look something like this in the ideal case. And the residence time distribution, which you dealt with in your first assignment, even though you didn't completely have the tools to do it, the residence time distribution in terms of time and C over C0 would look like this. And that's for kind of idealized case of plug flow. If we have fluid moving at an advective velocity which is equal to length over time, then we could write length as being equal to advective velocity times time. And so that's kind of what this would be. And this is at time t1. I guess this would be, in terms of time, just manipulating this would be equal to length over velocity. when it breaks through. So this is the upstream boundary condition. This is what it looks like in the sample. This is what it looks like as it comes out the other end. And we can think about a couple of different things. So if the dispersion is equal to 0, then this is exactly the green curve comes out of it. If the dispersion is not equal to 0, has to be positive, then it would look like this for the same input function. And I guess the output would look like this. And so all the diffusion means is that there's an extra mechanism that's different from the bulk plug flow of this front, and it spreads things ahead of the front, and if it's pushing mass ahead of the front, it means it has to lose mass behind the front. And so I suppose you can think of this as being flow within a porous medium where you have all these fingers that would represent the front, where you have on average these fingers of solute that are ahead, that if you take an average, then on average it's at the middle concentration. Ahead of the front, if you took an average here, it would be mainly water. And if you took an average back here, it would be mainly solute. That's all that's saying. So that would be physically what it looks like. A bunch of fingers, heavy in solute in the solvent, and some which are just pristine water in between them, so that when you take an average, which is what we're doing along the length of this core, it would look like that. So that's what we know about this system. I guess the other thing that's worthwhile mentioning, and I'll draw it on a separate curve, is that, actually I'll draw it below it, and it's an important one, and that is that what I just drew on that curve isn't completely true. And we talked about using some models that look like that behavior, and if I draw that here, it's going to look a bit like that curve. And this is time. And so in real systems, this is only this plug flow behavior and this steep front with the 50% concentration in the middle of this length. This is only true for Peclet numbers, which are advective velocity, diffusion coefficient over length, greater than about 10, I think we said. That's not right, that's not the right definition. Switch D and L, and then you got it. Yeah, has time in it, so this is DL. And so this is only true if that's the case. And so what we can do is we find that we can represent this equation as a function of three unique parameters. One is C over C0. One is Peclet number, which is velocity times length of flow. This might be the length of flow, or it might be this actually, divided by dispersion coefficient. This is Peclet number. And I think we call it T sub r, a relative time. It's actually a pore volume, which is advective velocity, length, divided by time. I'm not doing very well today. So velocity times time is the length traveled in a unit time due to the advective velocity, and length is the length where you are. And so if you're at the location where this is equal to 1, this is equal to actually 1 pore volume. It means that you've pushed a volume of liquid water in the top end that has now arrived at the downstream end when this is equal to 1. That's the physical meaning of this. And so what we can do is you can write this equation in terms of C over C0, which we said, T sub R, bless you. This is then equal to 1, which is, you can think of it as if you introduce a dissolved tracer here at time 0. Once the water that you're pumping in from upstream has completely displaced the old water in this core, 1 pore volume, then it's arrived downstream at 1 pore volume, and the concentration should immediately go up to the stuff that you started pushing in. And the use of doing this is that if you solve this equation properly, not assuming that it's going to be this, then it looks slightly different. And the relationships come out like so. So this would be, the green is a Peclet number equals infinity. This is a Peclet number of 1. And this is a Peclet number of 0.1. And so the faster the flow is, it approximates plug flow, if this velocity is fast. And the slower the plug flow, the slower the flow, immediately it looks much different from that, and we can characterize that. And so, if you, the key figure that looked at that behavior, if I can find it, it should be just before this. No? No. All right, must have been 3.1, at the end of 3.1. Is this one out of Feder? I don't know whether a big proportion of you have Feder or not. That's exactly this expression. So if you plot those analytical solutions, I looked at the videos, I saw that I did. So a Peclet number of infinity plots on this graph is this point here. Peclet number of 100 is this one here. There's 3 curves because there's 3 kind of different boundary conditions. A Peclet number of 10 is this red curve here. And you see they kind of go through the 50% mark, right? This bullseye here, roughly. But once you get to a larger number, when this must be a Peclet number of 1, then it bears nothing like this step difference. So that's important. It means you can use these curves. If you calculate your Peclet number, which is smaller than 1, then it just means you have to use some assumption that doesn't include this plug flow moving through, where this immediately gives you the location of the front according to this 1 pore volume. That's all it says. So that's an important concept to think about. And so I think it's, even if I say so myself, I think it's reasonably explained in the videos from 3.1 and 3.2. But that's I guess the punchline, I would say, from what came out of that class. So be aware of the fact that if you solve the PDE that represents these processes, then your curve that we just looked at is this, which isn't necessarily the same as this. You can get away with assuming for Peclet numbers bigger than 10 that the 50% concentration will be about at the location of where the front should have gone based on this very simple velocity relationship. But if the Peclet number is smaller than 10, then these curves are different. And you have the equations to do it if you need it, but you should be aware of that, because that's important. Okay? So that's kind of the beginning punchline, if you like, for today. And that says that the behavior you expect to see in the field is controlled by a couple of different things. It's controlled by dispersion, and it's controlled by the advective velocity. So if you want to have any chance of being able to say what's going on under your feet in the field, you have to have some way of being able to figure out exactly what these two important components are. And so it comes down to saying, what experiments would you do to be able to evaluate the magnitude of this d sub L parameter? So we want to figure out exactly what this is. We know it's a function of molecular diffusion and a function of advective velocity. And so we might need to figure out how to do that. And so there's three things we could do. And I'm going to talk about them kind of in overview, because the first two aren't very useful for reasons that we'll talk about. And the third one is much more useful, but is only present if you have a previously contaminated site, which you might not always have. And so we'll talk about approaches to get dispersivity. So how would we try and measure this value for DL? So what you could do is, if you could go into the lab, you could take a core and you could run exactly the experiment we ran just now by flowing water through the core, doping it with a tracer, and waiting for it to arrive at the downstream end, and plotting up the concentration change as a function of time. Because you can't see into the core, right? It's opaque, so you won't be able to see exactly this evolving plume, but you can get the output behavior, and you could try and fit this output behavior with this curve that we have here. That's basically it. That's really what we're going to try and do. So you take the concentrations in the downstream at a bunch of different times. You'd fit it onto some curve, and then if you had that curve, you have a unique curve for each Peclet number. So if it fits a Peclet number of 1, then you have that. You know that's equal to the advective velocity times times length over d sub L. You know how long your core is. You have control over the rate at which you're pushing in fluid. You know the value of this. It might not be 1, but it might be 0.1, because they're all unique curves. And so the only unknown you have is d sub L. And so that's exactly what you'd do. And so if you look at I'm going to skip this, doesn't make any difference. This is just basically an explanation of this. You'd run an experiment, you'd inject water flowing at some rate, you'd put a dye or fluorescein or some dissolved component of hydrocarbon in that you can detect at the other end. You'd measure its arrival time versus time. You'd fix it to one of the analytical curves we just looked at, and you'd get the value for DL just as we said. Nothing different from that. So yeah, this is it here. And so the equation that governs that is this term here. U is the number of pore volumes, I think. Yeah, U is equal to TR. And you remember TR is equal to advective velocity times time over the length of the core. So you know all the values of U. And so you could plot these curves directly from that equation. They're exactly the same curves that we talked last Tuesday in 3.1, if you watched it last Tuesday. And I think perhaps it was last Thursday for the calculations. And we just programmed it so you'd look at these individual curves from a relatively simple program. This is the complementary error function, not on all calculators, but certainly it's in MATLAB and maybe even in Excel, I'm not sure. And allows you to fit it.
I have a question. So,
Yeah.
In the equation, is that V sub A or V sub X?
V times X.
Oh, okay.
This is advective velocity. Actually, it's Vx. Velocity in the X direction. It's Vx, which equals advective velocity. What we've called VA. which is Darcy velocity divided by porosity. So, yeah, fine. And actually it's a derivative of Peclet number, right, as well. So Peclet number is equal to velocity times L over D. So that's this term here. This is 1 over Peclet number. And so this is dimensionless. So the Peclet number is the ratio, just like Reynolds number is the ratio of inertial to viscous forces. This is the ratio of advective flux. Flux is just a fancy word for the mass rate divided by diffusive flux. In other words, the flux carried by mixing and fixed wall. So that's what Peclet number is. And so, well, I don't think you need to use that, but it's there. It's just the same. It's a derivative. It comes out of some of the expressions that we talked to on Thursday about. So you run your test, you plot your data from your test, you see which of these curves it fits on. This gives you a Peclet number. And if you know what the Peclet number is, and you know the velocity length over dl, you know the velocity and vector velocity you're putting in at, you know the length of the core that you're sampling, and therefore you also know the magnitude of the Peclet number, and the only thing you don't know is this. So having spent 5 minutes saying that you could do that, I now will follow by 5 minutes saying that you probably never will. And the reason is that when we talked about the form of these curves, I drew this little fingered diagram at the bottom. So a solute finger, water in between as it moves downstream. And so the reality is that this mixing, so in other words, this vertical value here, the green one, means dl is equal to 0. The gray one is dl greater than 0. And so as it becomes more dispersive, this inclination of this curve gets flatter and flatter, meaning that there's more mixing going on. And so the reality is that this mixing is due to the fact that in an aquifer you get lots of lenses of contrasting permeability, maybe by deposition. And so the solute will tend to go down the fast flow channels, and those will advance the tracer much faster than in the intervening low flow velocity layers. And so this dispersion, this whole behavior, is a function of this kind of mixing with fast highways and very slow highways for transport. And if you take a core out of an aquifer, which might be a small portion of this, you don't get that structure embodied within the core, and so you don't get this behavior embodied within your experiment that you do. And so doing your experiments in a core that you take from the laboratory, if you're looking at advective flows at relatively high Peclet numbers, they won't give you the right amount of dispersion. They'll always underestimate the amount of dispersion, and so they're not very useful. What they are useful for is if you are storing low-level radioactive waste in a clay barrier, and the only mechanism by which the radioactive components can get through that is by diffusion, no advection but by diffusion, then your experiment will give you exactly the right answers because it's representing the real behavior that you have. But if you want to represent advective fluxes, it won't be very useful for you. So scale is important, and the whole essence of that behavior is related to scale. So the other option is to do what's called a single well tracer test. Not very useful either, not very often done. And the whole idea is this. You have a borehole, you inject fluid in there with a tracer in it, And so as a function of time, and if you look at the motion of that tracer relative to this central zone here, is you'd get motion, and if this is c over c0, then you'd push the tracer in over a period of time. If it was plug flow, it would get this far in a given time, up to this boundary. This would all be saturated by the tracer. And then you recover it back to the borehole, and you look at the change in tracer as a function of time. So the diagram I just drew on the right is in space. The diagram I'm going to draw on the left is with respect to time. So what would this look like? It would go in like this. I suppose if you then start withdrawing it at time t1, then what's the concentration going to look like? It starts off here. It would go on to some amount here. And then once you've recovered all of this mass of solute, it would then be water that comes back into your hole at zero concentration. So that's what it could look like. If it's a real aquifer, I guess you might expect it to look a bit more like this, right? This dispersion at the front. So now, if you recover it, you'll bring it back, but I guess you'd see a manifestation of that behavior here. And so, in the case that you had dispersion being equal to 0, let me do it in red. Dispersion greater than 0, and dispersion equal to 0, then the responses that you get here would be different. And so the fact that you get this response with this not vertical angle but a canted angle is a measurement of the dispersion. So if it comes back as a plug flow, you know you have no dispersion in the system. If it comes back with an angle attached to it, then you have increasing magnitudes of dispersion. And if you have even more dispersion, then it would come back presumably even flatter. This would mean that initially its distribution would perhaps look like this. Not a very well drawn curve. I'm just going to draw a straight line. Perhaps the curve would look like this. And then a recovered curve might look like this. So the gradient of this curve, or the shape of this curve, is indicative of the dispersion. And that's what we want to determine. And so we could use it in that way. And this is an expression that allows you to be able to do that. It's the same as the expressions we had before. This is the number of injection pore volumes. This is the number of recovered pore volumes. You'd inject a certain pore volume, then you'd recover the pore volumes. So this would be a changing number to be able to plot this curve. And it's a function of this dispersion, the radius of the plume as it went out from it, and other things. But it's not very satisfactory. And so the reason that this isn't very satisfactory is that your injection, instead of being at millimeters or centimeters per day in terms of flow, this might be at millimeters or centimeters per second. So the velocities at which you inject are much larger. And if we know that the magnitude of dispersivity is equal to the diffusion component plus alpha advective velocity, if this is a big number, then the results are going to be sensitive to the magnitude of the velocity that you use, which are not representative of real systems. And so it's not very useful in that regard. So I'm giving you all the reasons not to use some of these methods. So the first one satisfies a scale problem. It's not representative of the aquifer, and therefore when you do the experiment on a sample core, it doesn't give you a useful representation of the aquifer. This one has a scaled velocity problem, because the injection rate that you're pushing it in at is usually much larger than what happens within the field. Your device battery is low. And so what you could do is do another version of an injection test. Again, it exercises a big portion of the aquifer, which is useful because we think that heterogeneity within the aquifer is important, but it doesn't do it in a homogeneous way. And so if you think about this, this is an injection well and a recovery well in plan view. These represent the streamlines between injection to recovery. The longest streamline is the one that goes to minus infinity and then comes back from plus infinity. Here. And so you know, if you took each of these stream tubes, so for instance, if I took the stream tube that looks like this, so this represents one stream tube, a bit like the flow nets you might have drawn in 452 if you still do that. So you could represent that stream tube just like the core that we've been taking. And so if you now draw on that core what the concentration would look like if you went from upstream to downstream, then it would look something like this, right? It's no different from what we had before. You could treat it as just a cylindrical sample that happens to be being squeezed into this confined component. So this would be the relative concentration, C over C0. I've run out of space, but this would be C over C0. So this is one of the flow channels. If you took another flow channel, say this flow channel here, which is this, and you stretch that out, then all of a sudden that flow channel's longer. And so not only is it longer, the pressure drop from here to here has to be the same in both of these, and so this advective velocity has to be slower. And so this plume then has to be traveling at a slower velocity, and so it will arrive later. And so if you think about it, all of these individual stream tubes will have different arrival times, and if you plotted those arrival times, it'll look a bit like the curve at the bottom. I can draw it here. So if we draw those arrival times as a function so if you had plug flow, the arrival would look like this. If you had plug flow along this little conduit here, it will arrive at some time given by the advective velocity and the length traveled, right? But only a portion of the flow is going to arrive this time. So a portion of the flow will arrive here. The flow that's coming down this stream tube will arrive much later. And so if you think about what that distribution would look like, it's going to look like this. It's going to have some curve. So this one arrives here. This one arrives later. The one that goes off in this direction and comes back in here is going to be even longer than this, so that will arrive later. And the one that goes from to plus infinity and back will be never reached, right? Infinite time. And so this will never quite reach that asymptote. And so the importance of drawing this out is that this curve looks exactly like the dispersive curve for flow within a sample like this. But it's not reflecting anything about the porous medium. It's reflecting only the fact that the geometry of this flow regime causes this artificial diffusion. And so this isn't a very useful test because the diffusion that you look like you see here, or dispersion, is not a function of the properties of the aquifer, it's merely a function of the flow geometry that happens to evolve in this. And so you can't reliably use these results very easily, basically because this flow geometry masks any innate effects of diffusion that are present within the system. And so a twin well tracer test doesn't work very well either. So we're kind of running out of options here. And so the third option is to be able to rectify the two shortcomings of the other methods. We said the core was too small, so it wasn't representative of the aquifer, and so that wasn't very useful. We said that the in situ tests sampled the right volume of the aquifer, but they're kind of tough to interpret. One for the push-pull test was that the velocities are too large compared to natural systems. And the one for the twin well tracer test is that a big part of the dispersion that you see is not due to the properties of the aquifer at all, but due to the geometry of the flow regime that you set up. And so both of those problems, size of the sample and representative of the flow velocity and the geometry of flow, are rectified, if you like, if you look at what are called natural gradient flow tests. And a natural gradient flow test is just that you need a contaminated site. This happened to be done at a site that wasn't contaminated, but was contaminated on purpose, on a Canadian Air Force base, Borden. And so a hole was dug, a mixture of, I think so, this is sodium chloride in this case. Salt was put in, and it was a very shallow aquifer that could be sampled by just pushing capillary tubes into the shallow aquifer a couple of feet and sucking a sample out. So you could get these very dense contour maps of the distribution and concentrations as the plume goes down gradient. So this is at day one, where the plume looks like, and it's the outlines of the minimum concentrations are given by this. At 85 days, it's this. So what's that? That's 3 months or so, is that right? Yeah, 90 days would be 3 months. At 462 days, this is the outer outline of the plume. And at 2 years, it's sitting up here somewhere, if you see these outlines. And so it's certainly sampling a big part of the aquifer, 60 meters. It's certainly moving only at the velocity that the fluids are natively moving in the aquifer. And so it's moving under the natural hydraulic gradient. So the gradient refers to the hydraulic gradient that's driving flow. So in other words, advective velocity is equal to K over mu, 1 over porosity, d pdx. And it's an unconfined aquifer, so really it's just the gradient of head within the aquifer. And so we can use what we know from our downwind gradient tests. So I think also on Thursday you'll have looked at this idea that you could release a dissolved component in a groundwater regime and it will move down gradient like a cloud, just like a cloud being carried in the atmosphere. As it moves down gradient, it will spread by dispersion. And the solution for this is very simple in that it gives you the magnitude of this spreading, this length, is 3 standard deviations. It's a Gaussian distribution. And these 3 standard deviations are equal to 3 times the square root of 2 times the dispersion times time. So you take this sample at a 647 days. So the time is 647 days. You measure the size of the plume, and immediately you're able to calculate the amount of dispersivity just by knowing the knowledge of that geometry. And so we can use that to our advantage here. Very straightforward. First of all, we want to know how far it's gone. We know at 85 days it's gone 9.5 meters downrange. At 462 days, it's gone 38 meters downrange. And at 647 days, it's gone 61 meters to the middle of the plume, the center of mass of the plume. So if we know that velocity is equal to length over time, we have both length and time, and so we have advective velocity, which turns out to be about 0.1 meters a day. Just using days as a convenient time rather than seconds. We also know that this expression gives us our dispersivity. We can measure these half lengths. So the half length at this time here would be some amount here. I don't know exactly what it is. That looks about right. 5 meters. If this is 10 meters down here, then this half length is about 5 meters. Happens after 85 days. Likewise, if you look after 462 days, the half length is going to be, this looks like the center of mass here. This looks like the half length. Do you believe me that it's 14 meters? And so we have this length, we have the time at which that was recorded, and we can get the dispersivity. So this is what we can get. And it turns out to be, just by getting those, the dispersivities would be in units of meters squared per day, and they turn to be something like and it's just pulled out of here. So this is for the longitudinal dispersivity. So this is the flow direction, obviously, is in this direction, in the x. But there's also spreading that occurs in the y direction. So we call this longitudinal dispersivity, transverse dispersivity. This is much less, but it relies on, of course, the magnitude of this length here. So these lengths here are now whatever these magnitudes. I guess I've used for this. This would be this. 6 meters at 462 days. I don't know if I believe that or not.
I have a question.
Yeah.
So how can we obtain the value of three deviation? The sigma value.
Oh, because the process of a normal probability distribution is exactly the same as the physical process of a random walk. A particle of a molecule that can go this way or that way or that way. What causes Fichtean diffusion? So the process that defines the normal probability curve, if I go back to it, the solution for this transport equation is just exactly the same as a Gaussian normal probability curve. And all that we choose 3 standard deviations for is that I think 3 standard deviations control something like 99 points, approximately, I think 99.7% of the mass.
So the half length is a 3 standard deviation in this case.
The half length is the distance to this fringe, including 99.7% of the mass. So the length that we use is 3 standard deviations. This is 3 sigma. Okay? Okay, great. Yeah, good question. So, yeah, so the length that we're using is the length in the plume both in the longitudinal direction and in the transverse direction. So the 3 sigma that we use also here be the same equation. I guess in this equation, the dispersivity in y would be equal to dy is equal to 3 sigma. I suppose we call it y, right? Because it's in the y direction. All squared divided by 18t. Just by rearranging this expression. The 3's and the 2's come out to be that. And so this length, this is the length. This is our 6 meters. And if we do that, we find out the transverse dispersivity is about 0.01. Just rounding it down. So these are the two magnitudes. So, and you'd perhaps have guessed that because one is a factor of 2 different from the other. I'm not sure if it comes through because there's a square in here. But the longitudinal dispersivity and the transverse dispersivity are different. This is about twice as much. Sounds about right. And that's manifest by the fact that this spreading in the longitudinal direction is much more than the transverse direction. And also remember that the velocities that we're using, I guess the velocity doesn't come into this term at all, really. But if we wanted to calculate from this now the magnitude of this value alpha, remember longitudinal dispersivity is equal to Fickian term plus alpha L V X A. So we have this, we just calculated this. Let's assume that diffusion is trivial in this system compared to the advective mix, the mechanical mixing. And so now we know what this is. We know it's about 0.1 meters a day. And so we could calculate the value of this parameter, which should describe our system, the Agar system. And the reason for writing out this is that if we want to calculate the transverse dispersion, this would equal, again, the Fickian component, which again would be essentially 0, plus the transverse dispersivity, but times the velocity in the x direction, right? This has to be the velocity in the x direction because the velocity in the y direction perpendicular to it has to be 0, just by being orthogonal. So this is the advective velocity in the downstream version, the maximum. They're the same. So if we wanted to, we could calculate the value of these two dispersivities, which are functions really of the aquifer that we'd like to know. Because if we have this, then we can do this calculation for different flow velocities. So if you take those data and you plot them, you end up with a curve like this. And this is kind of a strange curve. So if you plot the length of the plume, so for our, this is the length of the plume. So if I draw a little, yeah, I guess it's how far the plume has gone. So this would be L. And if you plot the magnitude of this longitudinal dispersivity that we've just tried to calculate from the Borden results as a length, then you get this kind of shotgun plot. This is on a log scale. This is log dispersivity. This is log length of the plume. Very long plumes as well, 10 kilometers, 100 kilometers. Not really engineering type plumes, but also 10 meters, 100 meters, kilometer. So there's a huge spread here, and they fall, if you like, between these bounds. And what's often quoted is the magnitude of the average line through those, which is this curve here. And the equation of this curve here is that the longitudinal dispersivity is equal to the length of the plume divided by 10. no particular aquifer, every aquifer, right? And so what physically is the constraint that's giving this that behavior? Well, it's the behavior that we kind of alluded to before, and that is if you think that the mechanism that is causing this spreading at the front of the plume is due to fingering, that some high, fast fingers go ahead, some slow fingers get delayed in the interstices between them. If you take the average at each of these locations and you plot them on our curve that we had before, then it kind of looks like our distribution that is like this. So this is x, this is c over c0, this is just averaging the amount across this part of the plume, etc. And so the conventional wisdom, I guess, is that if you have an aquifer that has this heterogeneity in it, then you'll see that in a small sample, but it would be very muted. If you now have an aquifer which is, you take a sample which is 10 times larger than that, the chance of you seeing a big fracture or a fault in it is now much larger than in your smaller sample, and therefore the dispersion is increasing. If you take an even bigger sample, which is now kilometer scale, the chance of you having a big fault in there, which is now a superconductor, is relatively likely. And so the observation that this dispersion coefficient changes with scale is just a manifestation of that. At small scales, the heterogeneities are small. At large scales, the heterogeneities are huge. And that it's that behavior that gives this kind of universal law which might allow us to constrain some of our results. And so you can use that, but you can use it with caution, because of course if you have a site where your plume is 10 meters long, then that means that if you want to constrain your dispersivity, then it could be between a value of 10 to the minus 2 and 10 to the 2. Right? And so this is certainly a best fit through the middle, perhaps a good estimate, which would give you 1 in this particular case. But the errors on that, or the spread, is just very large. And so it's useful to use. It's a number that you can use, and you should use. But it's kind of disconcerting because it's completely independent of any of the properties of the porous medium that they were going through. It has no information about the porous medium in there because it just includes a scale, a length scale, and a magnitude of an output parameter. And so all we can suggest is that the reason for that is due to this kind of process behavior that you get a larger and larger sample, that a bigger and bigger plume samples a bigger and bigger part of the aquifer, and therefore the heterogeneity in that bigger sample of the aquifer is larger. And therefore if this is due to heterogeneity, then the dispersion coefficient should concomitantly be larger as you go along this. That's it. So that's the punchline. Oh, I thought we were going to get done earlier today. We're a minute off, I think. And that's it. I think I want to be right where I am. So what we've talked about so far has been what we'll call conservative transport. And conservative transport means that the mass of solute that's in water is conserved within the water and isn't removed onto the porous medium it flows past. It turns out that DNAPLs, once they dissolve in water, are actually quite reactive with the porous media they go through, and therefore they are attenuated by being attached to the porous media, and the rate at which they go down gradient is retarded, slowed, versus a conservative plume. And so the next thing we'll talk about is transport for real materials that have that kind of behavior attached to them. Okay, that's it.